All right, Taylor and Maclaurin series. Taylor series and Maclaurin series are the same thing. Maclaurin just happens to be when you plug in 0 for C into this giant mess of a formula. But the point is they're both the same thing. And what you're going to use them to do is to approximate stuff. Now when we say approximate, I'll get into a minute what that means, because you may recall we did linear approximations and Euler's method previously in calculus. So this is just going to be like a better way to approximate stuff than assuming everything is a line. Again, we'll get that in a second. You should really think of these problems, though, as an exercise in plug and chug. So the first thing you want to do is get used to this formula and start memorizing it. And I know this thing looks pretty intimidating. It's pretty crazy. But if you start looking at the terms, they're all, if you just start numbering at 0, like this, consider this the 0 term, the 1 term, because it has a power of 1 essentially. This is the second term, the second degree term, because it's got 2's in it, third term, etc. You'll notice that whatever term number you're on is what all the numbers are. So the second term, second degree term, has a second derivative, a 2 factorial, and a power of 2 on the x minus c. The third term has a 3 factorial, a triple prime, and a power of 3. Fourth term has 4 primes, 4 factorial, and 4 right here. So there is some consistency to the pattern, and it turns out it actually extends back to these first 2 terms as well. You could just memorize there's always an FSC out front, and in the next slide when I show you how this is kind of an approximation anyway, it might actually make sense that there's an FSC here, but this one is pretty obvious. You know, if you want to, you can just slap a 1 exponent on anything you want. It is a single derivative, first derivative. And then if you wanted to, you could throw a 1 factorial underneath, just like all the other terms have factorials. Hey, why not throw a 1 factorial? And oh look, 1 factorial is just 1, which didn't mess anything up, right? The only reason it wasn't drawn in the original formula is because 1 factorial is 1, so why bother? The 0 term you can actually get the same way, because if we sort of took the pattern here, where we take a derivative with no primes, you know, so if we plug in 0 for the primes, that would be no prime at all, which is f, just the original f with no derivative aspect to it. If you raise your x minus c to the 0 power, you would just get 1, so that's why there's no x minus c here, there's just a 1. And then if you throw a 0 factorial underneath it, 0 factorial is actually 1. And that's kind of one of those weird by definition things, kind of like anything raised to the 0 power is 1. 0 factorial is also 1, which is kind of funky, but it sort of explains how each of these terms is really just like all the others. Alright, so that's the formula. Plug and chug, memorize that puppy, and let's get into a little bit of how it works and generally why this is an approximation. If you just want to really take my advice and go plug and chug, I guess you could skip this video and go to the next one, but hey, we are going to work a couple of example problems here, so it doesn't hurt to ease into the pool a little bit more slowly. So the first thing I want to say is, you know, what is an approximation? So I mentioned before back in calculus, earlier in calculus, we used derivatives, and sometimes we called them differentials, to estimate values of functions. So like let's say you knew that the exponential function, just e to the x, you know it crosses the y-axis at 1, because e to the 0 is 1. But then let's say you wanted to figure out what e to the 0.1 was. So what's a good way to approximate e to the 0.1 without a calculator? Well, what you could do is you could take the derivative at 0. So we could sort of like, since we know this point 0, 1, what we did was we drew a line, the tangent line to the curve at that point. And the tangent line kind of went like this, and it shot off like that. So now if we want to know e to the 0.1, let's say this was 0.1, we can't get 0.1 exactly because we don't know the exact values along the curve, but we could just say, you know what? Let's find the equation of this tangent line and plug 0.1 in for x on that, and we'll get this point. So instead of getting the point we want, which is on the actual curve, we'll get the point right below that that's on the line. And it's really easy to find a point on a line, right? Because we know the equation of the line. We use the derivative to find its slope. And all we're going to do is just kind of do essentially a rise over run calculation right here, go sideways then up. And that's how we get that point. And that's the linear approximation of the exponential. And we could do that to any function. If we wanted to, if we happen to know a point right here, we could draw the tangent line right there, and use that to estimate this point. The problem with these linear approximations is they get pretty bad pretty fast. So if you wanted to find e of 0.8 or something, which is obviously further away, if the only point we knew was this one, and we follow that same linear approximation out to the right until we get to 0.8, it's like, wow, look at how bad that approximation is, because it's way down here, and the real point's up here, so our error, the error of our approximation, that delta y, is kind of big. So linear approximations kind of suck a little bit, because unless you're really close to the point that you took the approximation at, where you started the tangent line, they get really bad really fast. So the question is, wouldn't it be great if instead of having a linear approximation, which is just a tangent line that we sort of pretend is pretty good, what if we had something that curved a little bit? Because boy, you know, I bet if I had a parabola that kind of went like this and maybe followed it a little bit closer, you know, this would be a much better approximation than this one was. And if instead of using a parabola, I used like a third or fourth degree polynomial, that would maybe even hug the curve even tighter, then maybe I get this point right here, which is right next to the one I want. So it turns out that that's what Taylor series are doing. And if we look at that formula again, you'll actually see that the linear approximation was this part. So just these first two terms would be the linear approximation of a function, because you're basically just going to take the y value that you know, and then you'll go a delta x to the right, and if you multiply that by, if you multiply the run by the rise over run, because remember slope is dy dx, the delta x's cancel and you just get a delta y. So this first two terms of the Taylor series is just the formula for a differential or a linear approximation. But then look at this term. Oh, look at that. Now I can't explain quite as straightforwardly in terms of rise over run or whatever why the second derivative would sort of help you bend that approximation line a little bit closer to the curve. But the point is, we know that f double prime is curvature. So if this thing's curving up, then yeah, the curvature would help you curve more in the direction you want to go, right? And that same thing keeps happening. These higher and higher order derivatives help us get that curve closer and closer to the real curve. But you'll notice that these factorials downstairs start getting pretty big. So you do most of your approximating in these first couple or three terms. By the time you're getting to the third term and the fourth term, you're way out in like the fifth and sixth decimal places. It gets, you know, they start becoming useless pretty fast. But the moral of the story is, this is an approximation, and we're using these higher order terms with exponents of 2 and 3 and 4 to make that tangent line bend into a tangent curve that really hugs the original function. All right, so let's do it. Let's try doing one. So we're going to find a third degree Maclaurin approximation of e to the x. So Maclaurin, this at 0, all that means is we're going to plug in c equals 0 to the equation for Taylor series. So all Maclaurin means is, hey, you know, the special case of when we're taking it around 0. And what that means is, when we say at 0, what we're saying is the point we know on the curve. Because the whole point of these series is, you know, if you know this point, you can use that to approximate points elsewhere on the curve. If we knew this point, we could instead use that point to approximate values along the curve. But at 0 just means, hey, we're plugging in 0 for c, meaning that this is the point we know on the curve. So let's just plug and chug through the formula. First of all, you'll notice there's a lot of derivatives here. I got f prime, well I got f of course, then f prime, f double prime. And third degree means we're going to go out to the cubed. The third degree one is this guy right here. So that means we got to get all the way up to the third derivative of f. So the best way to start these problems is just whip up all your derivatives real quick so you have them to work with. So you know that f equals e to the x, because that's what we're approximating. Then f prime is just the derivative of that, which is, guess what, e to the x. And then f double prime is e to the x, and f triple prime equals e to the x. And I think that's the last one I need, because that's the third degree term has a triple prime. All right, so now we can just plug and chug. So the function, the third degree polynomial, also known as P3, meaning the polynomial of third degree, it's going to be f of c, so that's going to be e to the, remember c equals 0 in this one, so this is going to be e to the 0, plus f prime of c, so f prime, we got to plug in 0, times x minus c, which is 0, plus f double prime of c, so again e to the 0, over 2 factorial times x minus c, which is 0. And then we need that third term, this guy right here, f triple prime of c, so that's e to 0 yet again, divided by 3 factorial. And oops, I forgot my squared on this puppy. I find that's, when I'm working these, the mistake I make the most frequently is forgetting my exponents, because there's so many things to write down. It seems like making sure I put the exponent on that parentheses is the easiest thing to leave out. Alright, so that looks kind of gnarly, except check this out. E to 0 is just 1. So I've got 1 plus e to 0 is 1, x minus 0 is that, so we just got x plus, again, everything, that's 0, or that's 1. So we got x squared out of that one, so we have 1 half x squared. And then from this term, e to 0 is 1, so we got an x cubed divided by 3 factorial, which is 6. Alright, so there you go. So we just found the Maclaurin series of e to the x, and we won't do in this particular problem, but what we could do now is having this, is that it turns out you can approximate if you graph this on your calculator. So if you graphed e to the x on your calculator, and then right below that, y2, you graphed this function, it turns out those two curves would kind of follow along each other pretty good. Like they're almost the same curve. You'd have a lot of trouble even figuring out which one is which. So if you want, in fact, they'd be on top of each other, so what you might want to do is, instead of graphing e to the x, graph like e to the x plus 0.1 or something, just to give it a little bit of a vertical offset so you can actually see the two and see that they're parallel. And then graph this one separately. So pretty cool. This polynomial and e to the x, very similar shape, which means that if you wanted to find e to the 0.6, not that you would really want to probably unless it was in a problem, but if you wanted to find e to the 0.6, instead you could just plug in 0.6 to this equation and you'd get a pretty close value, like out to several decimal places. And if you didn't have a calculator on hand, instead of using 0.6, maybe you want to use something easier to multiply, like 0.1 or something. So if you want to find e to the 0.1, you could actually work that by hand. Because powers of 0.1 are pretty easy. All right, hey, since we mentioned it, why don't we do it? All right, so if we want to approximate e to the 0.1, now you notice it says use the third degree Maclaurin series of e to the x, which is the problem we just did. So I just copied that series right here. And we'll approximate e to the 0.1. So e to 0.1 equals 1 plus 0.1 plus 1/2 times 0.1 squared plus 1/6 times 0.1 cubed. Now 0.1 is a nice one, like I was saying, because 0.1 squared is 0.01, so this is 0.005. And then 0.1 cubed is 0.001 times 1/6 is going to be I'm going to guess 0.00016 roughly. 1/6. All right, so you can see that as we add these up, our first term is large, it's 1. Second term is pretty good size, 1.1. By the time we get out to our third term, so only our second degree term, that only added 0.005 to our number. So we approximated this as 1.1 after only 2 terms, and after 3 terms, we're just at 1.10516. I obviously worked that on a calculator. Although you didn't have to. I mean, you could have just whipped these up. Anyway, the point is that our third degree approximation is 1.10516, and our first degree approximation, just the linear approximation alone, was 1.1. So in this particular case, the linear approximation was awfully good. But that's what we'll ask you to do, is just find an approximation of something. All right, so similarly, we could find a second degree Taylor series. Now, what's the difference between Taylor series and Maclaurin series? The Taylor series is not going to have 0 for c. So when you see the word Taylor, that's your tip-off that, uh-oh, I got to plug in something for c. And then the other tip-off is they're going to say at 2, meaning they want you to plug in 2 for c. So c equals 2 in this case. And then they want us to approximate something, e to the 1.5 is obviously not very close to 0. So maybe this will be a much better approximation of e to the 1.5 than e squared would have been. All right, so let's plug and chug. Once again, I've got all my, I learned last time that if f equals e to the x, then so does f prime, so does f double prime, and we're only doing second degree this time. So let's plug and chug. So e to the 1.5. I should have not written that yet. I should have just said e to the x. So basically our approximation of e to the x at 2 is going to be f of 2. So if we plug in 2 for there, we get e squared. And then f prime, which is going to be e squared as well, times x minus c, and c is 2, plus f double prime of 2, which is once again e squared, 2 factorial is 2, times x minus 2 cubed. All right, so if anybody's curious, so we can obviously plug and chug through this. At this point, since this is the Taylor series centered at 2, so basically if you look at the graph of e to the x, what this is doing is we're taking the point at x equals 2, there's e squared, and then we're coming up with our tangent line or tangent curve or whatever approximation at that point. So if you're thinking back to linear approximations, we're sort of taking the tangent line at that point, and then with this extra term we're kind of bending that tangent line into a little bit of a curve. But the point is that we're sort of basing our approximation at 2. It's going to be right on the graph at 2. So when we want to find e to the 1.5, we're going to be plugging in 1.5 for x. So e to the 1.5 is going to equal e squared. And we can actually factor out that e squared if we want. So maybe it'd be 1 plus x minus 2 is just going to be 1.5 minus 2 is negative 0.5, sorry, plus 1/2 times negative 0.5. But that is squared, which will make it positive. All right, so if we work all that out, we get a total of 4.618. Now you're probably thinking to yourself, hey, how good is that? I mean, the whole point of these approximations is that we don't have to use a calculator, right? I mean, that would seem like a good thing to be able to do. And so it's annoying that there's an e squared in there. But e squared you could figure out by hand if you wanted, because you know that e is 2.7 something. You could look it up, So if you wanted to find out what e squared is, you could multiply 2.7 whatever times 2.7 whatever by hand and get a number. And then this is obviously just going to be a decimal. So you really could work this out by hand if you wanted. Whereas e to the 1.5, good luck. Like how do you take a root of something by hand? You can't. It's an irrational number. You just have to come up with it. All right, so hopefully we learned one thing from this general video, which is that when they say, when it's a Taylor series, they're going to have to give you a number that you're centered around or at, and that's going to be the at 2. So that's just what you're plugging in for c everywhere. And other than that, you just want to come up with a list of the function and its various derivatives, and then plug and chug. And for those who are curious, you might be wondering, what does this x minus c really mean? Well, basically, if we're starting here and our approximation is based on 2, then you'll notice that we went 0.5 to the left, because the number we wanted was right here. So we were finding this point. So this distance right here, this lateral distance, that is x minus c, right? So if you're going back to your linear approximations, your run, the horizontal move you're making from the point you know to the point you want to know, is x minus c.